This video is part 5 of Chapter 3, Sensation and Perception for PSY 110S, the Psychological Sciences. Now we're going to move more strongly into understanding how perception works. Remember that the raw sensory stimuli that are out in our environment are just that, they're raw. What we do with the brain, though, is we have to combine lots of information, not just about those raw sensory signals, but also we have to integrate that information with what we already know about the world around us. Now, your authors made a decision to focus this latter part of the chapter on vision. Frankly, it's the sensory system that we know the most about as a field. Our two dominant sensory systems as a species are vision and hearing, and the visual system is one that we have spent, as a field, the most time studying. So remember that sensation is just information gathering, where you're pulling in physical stimuli and then recoding it through the sensory structures, and then sending that information on into the brain. Perception is that interpretive process that the brain goes through to make sense of sensory information. They basically work together interactively to give us a sense of what's going on in the world. Now, there are two different types of processing that are going on here, bottom up and top down. So we need to look at both of these types of processing to understand how we make sense of what we see. Bottom-up processing is essentially pulling in incoming sensory information as it moves through the sensory structures to the brain. It's called bottom-up because what you're doing is taking information from the outside world and moving it up to the brain. This starts with that transduction process of incoming sensory information. So in terms of vision, you're talking about light, and those transduced signals are then sent on to the brain. The top-down part is the brain using what you know, what you've experienced in the past, what you believe to be true, what you expect to be true, to interpret what it is that you are seeing or hearing or touching or whatever. It's called top-down because what you're doing is taking your previous knowledge and using it to inform your interpretation of what's happening in the lower sensory structures. Now, we know that, in the brain, there are more top-down connections than there are bottom-up ones, by about a 10-to-1 ratio. So to understand the difference between these two types, think about listening to someone speak a language that you don't know. You have bottom-up processing. You hear the sounds. You can't interpret that input, though, because you don't have the top-down processing information, the knowledge of that particular language, in order to make sense of what you're actually hearing. Perception has a subjective element to it. We often have that phrase, seeing is believing. Not always. Visual illusions are a key example of why that is. Perception is subjective because specifically of top-down processing. What you know, what you believe, what you expect is going to shape what you actually perceive. One example of how this can be problematic for us is when we experience something called perceptual set. And this is where you have an ambiguous stimulus and you're trying to make sense of it, and your previous experiences are kind of nudging you, if not outright pushing you, to perceive what you're seeing in a particular way. Another kind of effect is something called a context effect or a contextual effect, where the present surroundings of the thing that you're trying to make sense of is nudging you again in the direction of a particular interpretation. Now, the example that you're given in your text is this famous image of eventually what will emerge as a cow face. Now, at first, when you see that, for someone like me, I actually, in my upbringing, my childhood, I lived on a farm. We had cows. So my guesses about this picture may be biased in the direction of seeing cowness much more readily than other people who have no such experience. Now, you could prime someone if you gave them a bunch of priming with images of farm animals. That may set you up to be looking for meaning in that image in that way. Or you could set up the particular context so that you could nudge the person in the direction of that perception. Now, context effects, what those refer to are, interpreting ambiguous characters by paying attention to other elements in the visual field that are going to inform what you see. So the examples that you're given in your text, they talk about how ambiguous characters composing second items in a series and then a fourth item in a series, they're going to be determined by the context created by the objects beside them. So in this series, where you have lines and dashes, curves, and so on, it depends on the context surrounding these particular things. So the object you're to pay attention to here is the letter B in the top line, the number 13 in the second line. Notice that they are identical. If you pulled them out and put them side by side, they would be exactly the same. A 13 in the bottom line because it's surrounded by other numbers. A B in the top line because it's surrounded by other letters. So depending on the context that surrounds the image that you're seeing, you will interpret it in a completely different way. Perceptual organization and constancy are, as your authors put it, essential to bringing order to the sensory input that surrounds you. The data has to be organized into meaningful wholes, and there's a whole school of thought called Gestalt psychology or Gestaltist theory that helps us to kind of understand the way in which these meaningful wholes are created. Often our raw sensory information is incomplete, but we perceive things as being complete. So this is the process by which we fill in those gaps. So the context of sensory information is going to be used to determine meaning. That's the contextual effect. This word Gestalt, it's a German word. It's a hard word to translate directly into English, other than to say it's an organized whole, where the final whole object is more than just the discrete parts that make it up. So there are some specific examples that you're given in your text of figure ground, closure, and subjective contour that kind of demonstrate these Gestalt principles, where the whole is greater than the sum of its individual parts. So figure ground ambiguity, and this is sort of the classic image of this. If your focus of attention is on the white portion of this image, what you are likely to perceive is a vase. If your focus of attention is on the blue parts of the image, what you are likely to perceive is two faces. So if you ask yourself, what do you see? Do you see two facial silhouettes or a white vase? Well, it depends on where your focus of attention is. Which aspect of the image are you putting into the ground, which would be the background, and which aspect of the image are you pulling forward as figure? And if you look at the image long enough, you will notice that it will go back and forth. Now that you know you can look at either, you'll see the vase pop out and the faces will pop out. The vase pops out and the faces pop out. You can see both, but you really can't perceive them both simultaneously. You can perceive them one at a time. When you switch your perception from one to the other, your brain is literally switching how that input is organized and interpreted. So when you see the vase is the object, the rest is the background. When you perceive the faces, the vase is the background, the faces are the focal point. With organizational and perceptual ambiguity, and again, this is a very famous image that's designed to show these principles. What you have in the image, you can either see an old woman. Here's the outline of her nose, her mouth, her eye, or a different image of a woman with, this is her eyelash, her cheek, her chin, her neck, some headdress she's got on, and a feather popping out of her head. So it can be either one, but not both simultaneously. So that's similar to what we've seen before. But the question you're asking here with perceptual ambiguity is, do you see the head and shoulders of an old woman or a young woman? Why does your perception keep switching? Well, essentially, if you're having trouble seeing the older woman, she has the larger nose, located below and to the left center of the figure. The jaw or the nose becomes the chin and jaw of the younger woman. Because there's no contextual information to determine the correct interpretation, your perception is going to keep going back and forth. Now, if you were supplied with information, like what if there was a story that you were asked to read, and this was the illustration to the story, and the story was about a young woman looking across a room, then your bias is going to be in the direction of perceiving the young woman whose face is turned slightly away from you. If, however, the story was about an old woman, you are more likely to look and see that image reflected back at you. Now, there is a tendency in researchers looking at images like this one, there's a tendency to see the young woman first, just because of the whole of the image and the way it is organized. But this tendency lessens, and here's the context effect. As people get older, they tend to start switching to an image that's more reflective of their own age. That's a kind of contextual effect. Now, subjective contour refers to how our brains kind of fill in information that doesn't really exist in our in the sensory signals that we're getting. So in this example of an image, the question you could ask is there a very bright white triangle that is on top of the black circles in another triangle? Well, in a literal sense, no. What there is space. But as you stare at it, you might notice that your brain is inserting lineness to complete that triangle. So that's what's referred to as subjective contour. It's created by your brain and its perception based on the collective information, where you have the circles with a chunk missing. To demonstrate this overlying brighter triangle is truly not there, cover up everything in the display but the horizontal blank center. And when you do this, you're not going to see any difference in brightness across the horizontal level of the center of the display. The whiter triangle is purely a brain effect of amplifying what you're perceiving as a shape that becomes completed because of Gestalt principles. Now, perceptual constancy has to do with, when we're looking at a full scene around us, we need to know that there is something called perceptual stability or constancy. With objects, my car, if it's close to me, is quite large. It's still the same size if it's 400 yards away. Now, in terms of sensory signals, the image is smaller, but my knowledge is that it's still the same size. My car doesn't become a matchbox just because it's really, really far away. So we have these, the ability to kind of override the literal sensory information that's coming in and say, no, no, it's not tiny, it's actually quite large, or the reverse. So there's perceptual stability in size, shape, brightness, and color. My truck is actually a very bright blue. In dim light, my eyes are not perceiving that bright blue, but I know that the truck is still bright blue, for example. For familiar objects, the perceptual constancy is in play. So if we know something about it, like I know how big my truck is and I know that it's very bright blue. I can vary the distances, different angles, different lighting conditions, and I still know that it has those traits. The perceptual constancy is has an adaptive function. It helps us to, once we know certain things about objects in our environment, we can fill in the blanks when the conditions for perception are changing. This helps us to perceive greater order. It helps us to feel greater consistency in the way we're looking at the world. And, you know, position also matters here too. Like I know that my truck has certain wholeness. If I can only see it from one angle, I know that the rest of the truck is still there. So it brings some added clarity and understanding to consistency within the world. Depth perception involves making guesses, making assessments about how far away objects are from us. Now, some people are very, very good at this. Some people are not as good. But generally speaking, we all have some capacity to perceive depth, given normal structure and function of our visual systems. Part of what helps us to see depth is what are called binocular depth cues. Since we have two eyes, our perceptual system is dependent on combining the images, and your two eyes see slightly different images because they're not overlapping. This is referred to as retinal disparity, and it's based on the fact that there is a discrepancy between the two images. The distance, as the distance from us increases, you're going to have less disparity between the two images. So the closer objects are, this is why if you hold your hand as far as your arm will stretch away from your eyes, there's less retinal disparity than if you move your hand closer. And do you notice how you get not only more blurring, but you start to see two different images of your hand. If you close one eye and then close the other, it appears like your hand is moving. That's retinal disparity. There are also monocular depth cues. So these are cues that only require one eye. One of these is linear perspective. So imagine you're looking at a train track. You're standing in the middle of the train track, no trains. But you can see that the lines of the train tracks appear to converge off in the distance. That's a linear perception cue. There's also interposition, which refers to the idea that if one object blocks our view of another, we perceive the blocking object to be closer to us than the object that it is basically in front of. Now, visual illusions help to demonstrate some of these effects, but also show us some of the holes in the literalness of our ability to see objects. Since we have this elaborate perceptual system, it is possible for it to make certain kinds of predictable errors. So in the first image, image A here, this is the Ponzo illusion, where you have these two red lines, and because of the adjacent lines produced here by the image of railroad tracks, so basically you have two lines that are at angles and they're converging in the distance. This creates the illusion that the top red line is larger than the bottom red line. If you took out the background image of the train tracks, you would not see the lines as being different. They would appear to be identical. So this is a situation where your brain is essentially tricked because of contextual clues. And in this case, it's perspective clues that are messing with you. In image B, the two monsters in the image, this is called the terra subterra illusion. I have no idea why. The two monsters are actually identical in size, but just like with the train tracks, you have the image with these cues that suggest distance and the shape of the tunnel. Those contextual clues are affecting your assessment of the size of the monsters in the image. So you have to convince yourself that the two bars and the two monsters are the same. You're going to have to remove the background. Once you remove the background, then it's obvious to your brain that they're the same image. With the background in place, though, the brain is basically misinterpreting the relative distance, and that affects our perception of the size of the objects. The Muller-Lyer illusion has some things in common with what we've just talked about, and here what you're looking at is the impact of having these surrounding image cues. In the Muller-Lyer illusion, two vertical line segments are equal in length, but you build a context with these arrow shapes. If the arrows appear to be pointing outward, it can make that vertical line look shorter than if the arrows are pointing inward toward the line, which appears to make the line look longer. So again, this is a situation where excuse me, our brain is tricked and misinterprets what it's seeing. So in both images A and B, you have two vertical line segments that are equal in length. However, the one with the arrow feather endings on the right appears longer than the one with the arrowhead endings on the left. In images C and D, like the first two images, this illusion is created by the brain misapplying the geometry relating to the retinal image size of the objects. Based on our previous experiences with things like corners and edges, we kind of pull that information in, and it suggests to us a misperception, essentially. Finally, the moon illusion. The moon is the same size regardless of how far away it is. It is the moon. It has its own size and mass and all of that stuff. However, our perception of the moon's size changes depending on how close to the horizon line in our visual scene. It appears to be much larger when it's closer to the horizon than when it moves farther away. So it creates this perceptual illusion that the moon is getting bigger as it sets or as it is rising on the horizon. The brain mistakenly enlarges it in our perception because the images of horizon and overhead moons in real life are actually the same. But the context of the horizon makes it appear larger. So again, our brains do this miraculous set of calculations and interpretations, and that's the way we are able to perceive our world in all of its richness. It is prone to certain kinds of predictable errors, though, and these illusions that I've just spent the last few slides on show that that is the case. And that concludes my coverage of Chapter 3.